So in today's video, what I have over here is a block on an incline, and attached to the block is a spring. And what I want to do is I want to pull the spring up the incline, and the spring is attached to the block. So what I want to find is how much do I have to pull the spring, or how far do I have to pull the spring until I can finally get this block to move. So let's say that on our diagram, let's say that the distance that I have to stretch the spring, let's call that the variable x. And that's the variable we want to find. And so x just represents the maximum extension, or the maximum distance I have to stretch the spring in order to finally get the block to move. So what I want to do is I want to find the maximum extension distance of the spring the instant the block begins to move. So I want to find an expression for the extension distance of the spring. And we're calling that extension distance, we're calling that the variable x. And we're finding that the instant the block begins to move. And also notice here that the surface between the block and the incline has friction. So the incline, let's say that the coefficient of static friction of the incline, let's denote that with mu subscript s, and let's also denote the coefficient of kinetic friction with a mu subscript k. And so the surface between the block and the incline has friction. And so since there's friction present on the incline, let's analyze all of the forces that are acting on the block as it rests on the incline. So there's the block. And the surface has friction. And so since I'm pulling the block up the incline using a spring, there's going to be a spring force which points up the incline. And I'll denote that with capital F subscript spring for spring force. And there's going to be a weight force which points downward, which is due to the weight of the block, which is the mass of the block times the acceleration due to gravity. And so as I'm pulling the spring up the incline, what's going to oppose that spring force is the friction that's present on the surface. And so as I'm trying to pull up the spring, or as I'm trying to pull up the block using the spring, what's going to prevent that from happening is the fact that the surface has friction. And so since the block is not moving, there's going to be a static friction force which points down the incline. And so the static friction points opposite to that of the spring force because the static friction will oppose whatever direction the block is trying to go. And so in this case, the block is trying to go up the incline because there's a spring force. So the static friction will point down the incline. So the static friction will oppose whichever direction that the block wants to move. And also there's a normal force which acts perpendicular to the plane. And so notice that the weight force, which is m times g, can be broken up into different vectors. So we can break up this weight force into two different forces or two different components. So one of the forces will counteract, or it'll be equal in magnitude to the normal force. Which is this line right here, the one in the dashed line. That opposes the normal force, but it's equal in magnitude to the normal force. It's just opposite in direction. And there's another component. This smaller dashed line represents a component of mg, or a component of the weight force, which points down the incline. So notice how I broke mg, or the weight force, into two different vectors. One points down the incline, the other points perpendicular to the incline. And so notice that in our original diagram, that the angle that the incline was at was given by the letter theta. And so since that angle is theta, we can draw in a theta into this free body diagram. So the angle between mg and the other component of mg is just theta, which is the same as the angle in the original diagram. So let's redraw this triangle that we broke up into components of mg, the weight force. So the hypotenuse is just the weight force, which is mg. And we know that the angle is still theta. Now let's determine what the values of the other sides of the triangle are. So notice how if we want to find this side of the triangle, that side is the adjacent side to that angle. And so the adjacent side to the angle, we would have to use cosine of theta, because the cosine of theta is equal to the adjacent side over the hypotenuse. So that side of the triangle is mg times the cosine of theta, because it's adjacent to that angle. Now what about this side over here that's opposite to the angle? Since that side is opposite to the angle, we would have to use a trigonometric function which uses the opposite side, which is sine of theta. because the sine of theta is equal to the opposite side over the hypotenuse. So we now have our two sides, we now have all three sides of our triangle. And so as we pull the spring up the incline, there's going to be a spring force. And so what forces oppose that spring force? That would be just the forces that are in the opposite direction to the spring force, which are static friction and the component of the weight force, which is mg sine theta right here. So the two forces that oppose the spring force are the static friction and mg sine theta, because those are the two vectors that point, or those are the two forces that point opposite in the direction to the spring force. And so those are the forces that prevent the block from moving. And so now let's analyze all of our forces, or let's analyze all of the sum of the forces, because now we have broken up all of our, we have analyzed the direction of each of the forces that are acting on the block, and we broke up each of we broke up the weight force into components. So let's analyze the sum of the forces that act on the block. And so notice that there's a spring force which points up the incline. That's the direction that the block is being pulled. And also we're considering that going up the incline is positive. And so since the static friction force points down the incline, that would be negative because it points down the incline. And the component of the weight force, which is mg sine theta, also points down the incline. So that would also have to be negative. And we know that the sum of the forces, or we know that by Newton's second law, so the sum of the forces equals the mass of the block times the acceleration. That's just Newton's second law, that the sum of the forces equals ma. But notice that earlier we said that we want to find the extension the instant the block begins to move. So at the instant the block begins to move, that means that the block doesn't have any acceleration, because at that instant there is no acceleration. So the acceleration the instant the block begins to move is 0. So we know that the sum of the forces just equals 0 because we want the moment the block begins to move. And so this entire expression right here, all of that is equal to 0. And so now let's expand out our equation. So the spring force is just equal to the spring constant, which is given to us, which was K in the diagram, times however far we are stretching the spring, and that's the variable x. And that's the variable we want to find. we want to find x minus the static frictional force, which is the coefficient of static friction, which we defined earlier as mu subscript s, and that's multiplied by the normal force. And we're subtracting that by mg sine theta. But recall that we now have a normal force in our equation. But the normal force, that's just equal to this vector right here. And so this vector right here, it points opposite to the normal force. And so remember back when we broke up the normal force, or when we broke up the weight force into components, we found the sides of the triangle. And so the side of the triangle, or the vector that points opposite to the normal force, is this vector right here, mg times the cosine of theta. Now that points opposite to the normal force, but it's equal in magnitude to the normal force. So we can just substitute in mg cosine theta for the normal force, and then we can solve for x. So the normal force is just equal to mg times the cosine of theta. And now we're still solving for x. So let's bring all of the other terms onto the other side. And now let's isolate the x by dividing by the spring constant. So now we have our final expression for the maximum extension distance of the spring the instant the block begins to move. And so this expression shows right here how far we have to stretch the spring in order to get the block to start moving.